It all starts deep underground and ends up in your stove. Geologists hunt for gas, drilling rigs pierce the Earth's crust, and an explosive cocktail of gas, oil, and water erupts from the depths. Next, separators that stratify everything down to the last drop. Compressors that push fuel through pipes stretching 300,000 miles. And finally, the gas is cooled to negative 260 degrees Fahrenheit, turning it into a liquid to be transported across oceans. But how does it not explode? And how is it made safe for your kitchen? Watch and find out how gas really works. It all begins with geologists searching for true treasures underground, natural gas deposits. And no, they don't walk around with shovels. They use seismic waves to understand where gas is hiding beneath the earth. Once a location is found, well drilling begins. Imagine a drilling rig that can reach depths of over 10,000 feet. The well diameter is usually between 8 and 30 inches, and drilling takes weeks. After drilling the well, steel pipes are installed to reinforce the walls and prevent the well from collapsing. Then comes the magic. Under pressure of hundreds or even thousands of pounds per square inch, gas, along with oil, water, and a bunch of impurities, rushes to the surface. For this, special valves, Christmas trees, are used to control the flow and pressure. When gas, oil, and water erupt from the Earth's depths, they resemble a dirty cocktail with millions of particles of sand, salt, and other surprises. To separate this mixture into pure components, engineers use separators. The mixture, under pressure of up to 500 psi, enters the separator through an inlet nozzle. The first task is to reduce the flow velocity so that gravity can take effect. An inlet deflector, a baffle that breaks up the stream and slows down the movement, is used for this. Imagine sharply braking in a car. Heavy particles like sand and clay immediately fall to the bottom, while lighter ones continue to move. In the separator, the mixture separates into 3 layers. The bottom layer, water and sand. These are the heaviest components. Water with salts and fine particles settles first. Oil is lighter than water, but heavier than gas, so it floats in the middle. Methane and other light hydrocarbons rapidly rise to the top. To speed up the process, separators sometimes have inclined plates or cyclone modules installed, which increase the settling area. For example, plates angled at 45 degrees cause oil droplets to coalesce and fall down faster. If oil and water form an emulsion, demulsifiers, chemical substances that break the bond between droplets, are added to the separator. Sometimes, vibrating screens are used to filter sand from the bottom layer. The gas, meanwhile, passes through wire mesh mist eliminators that collect residual liquid droplets. Float level sensors monitor the thickness of the oil and water layers. If there's too much oil, a valve opens and it flows into a collection tank. A gas valve at the top regulates the pressure so that the gas doesn't exit too quickly. The ideal pressure is between 100 and 300 psi for effective separation. A sand dump valve periodically opens to remove sediment from the bottom. A typical vertical separator for gas fields is 20 to 40 feet tall. That's like 2 or 4 giraffes stacked on top of each other. The diameter is 4 or 5 feet, roughly the diameter of a circus ring, and it's capable of processing up to 10,000 barrels per day. A separator is a complex device where physics, chemistry, and mechanics work together to create 3 separate streams. After all, if gas contains liquid droplets, it can damage pipelines through corrosion or hydraulic shock. And 1% water and gas reduces its heating value by 5, or even 7%. That's like adding gasoline to your latte. Oil from the separator is sent to storage tanks, water is purified or re-injected into the formation, and gas heads to dehydration units. Some gas components, propane, butane, ethane, can be separated out. To do this, the gas is cooled to 150 degrees Fahrenheit, and these components condense. They are collected in special tanks and sold separately. For example, propane for grills or butane for lighters. Clean gas isn't ready for its journey yet. It needs to be compressed to a pressure of 800 or even 1,200 psi to be pushed through mainline pipes that stretch for thousands of miles. Compressor stations, true giants with engines producing thousands of horsepower, are used for this. Gas moves through mainline pipelines with diameters ranging from 24 to 48 inches. They run underground at depths of 3 to 6 feet, and their length can reach thousands of miles. Compressor stations are located every 50 to 100 miles to maintain pressure. When more natural gas is extracted than is currently needed, it isn't just vented or left idle. This valuable resource is stored in special underground storage facilities, which can be imagined as huge banks for gas. The most common types of such storage are depleted oil or gas fields, as well as salt caverns, located at depths of up to 3,000 feet underground. Depleted oil fields are cavities left after oil or gas extraction. They have natural geological barriers that prevent gas from escaping. Gas is injected there under pressure through special wells, where it is stored in porous rock, filling the voids previously occupied by oil or water. A single well can produce up to 10 million cubic feet of gas per day. Salt caverns are artificially created cavities in salt formations. They are formed by dissolving salt with underground water, creating large voids that are ideal for gas storage. These caverns have high integrity and allow for rapid injection and withdrawal of gas, making them very effective for regulating supply. Underground gas storage is very important for the stability of the energy system. In winter, when gas consumption increases due to heating, additional gas is withdrawn from these storage facilities to meet consumer needs. Similarly, during peak load periods or emergencies, these underground banks help prevent supply interruptions. Storing gas underground is also economically advantageous, as it allows for balancing production and consumption, reducing costs for surface transportation and storage. It's a reliable and safe way to ensure that gas will always be available when it's needed most. The length of gas pipelines in the United States is over 300,000 miles. Before gas reaches your home, it undergoes another check for purity and pressure. At distribution stations, the pressure is reduced to 0.25 psi, which is safe for home stoves and boilers. For safety, a special odorant, mercaptan, is added so you can detect a gas leak. At all stages, from the well to your kitchen, gas is monitored by pressure, temperature, and composition sensors. In case of an emergency, valves shut off the flow in seconds. Personnel undergo training, and systems automatically record the slightest deviations. Besides homes, gas is supplied to power plants, factories, and chemical plants. For industrial consumers, the pressure and volume are higher. Pipes with diameters up to 48 inches and pressures up to 1,500 psi are used here. Gas can be liquefied. It's cooled and transported by tankers across seas. First, the gas is compressed, meaning it's made very dense, like when you squeeze the air in a balloon. It becomes smaller in volume, but warmer. Then, this warm compressed gas is passed through special coolers. After that, the gas is passed through special devices, expanders, which allow the gas to expand and cool down even more, like when you let air out of a balloon and it becomes cold. Thanks to this, the gas cools down significantly, to about -260 degrees Fahrenheit. When gas cools to such a low temperature, it turns into a liquid, like water, but very cold. This liquid gas takes up about 600 times less space than in its gaseous state, so it can easily be stored in special tanks and transported by ships. Imagine this. By 2030, the entire world could be threatened by over 12 million short tons of spent lithium-ion batteries. But what actually happens to electric vehicles once they reach the end of their service life? It is not just simple disassembly. It is a high-technology process where even the remaining battery charge is used to power industrial facilities. Meanwhile, steel, aluminum, and plastic go right back into manufacturing, giving a new life to old automobiles. Watch until the end. You will be surprised by how efficient this recycling has become. The cost of electricity for charging is significantly lower than the cost of gasoline or diesel fuel, and the motor runs rather quietly. This, of course, increases the comfort of the ride. The most popular models are produced by Tesla, but there are many other manufacturers on the market, including Nissan, BMW, Audi, Mercedes-Benz, Volkswagen, Porsche, Rivian, Ford, General Motors, and Hyundai, which is quite a lot. However, even an electric vehicle eventually reaches the end of its service life. When the vehicle arrives at this end, it is sent for recycling. First, the car is deregistered, and then it is taken to special facilities that handle disassembly and recycling of vehicles. These can be recycling centers, auto dismantling sites, or recycling factories. Vehicles may be delivered by the owners themselves or by dedicated services that pick up damaged or non-operational cars. Some facilities work with insurance companies or government organizations that coordinate disposal programs. When the car arrives at the site, it is initially inspected to determine which parts can be reused and which must undergo complete disposal. The site is typically an area equipped with bays or specialized zones where all processes take place. Mechanics and equipment operators work here, removing vehicle components both manually and with the help of machines. First, all technical fluids are drained. The car is placed on a special lift or in a separate drainage area. Operators use pumps or remove drain plugs to extract motor oil, transmission fluid, antifreeze, brake fluid, and fuel. The fuel is pumped out with vacuum systems to prevent fire hazards, and the motor oil is collected in containers for later recycling. After that, the disassembly of the vehicle begins. The battery is removed first and sent to a separate recycling process. There, it is tested to determine the level of remaining charge and suitability for reuse. The removal must be done carefully, as the battery contains toxic and flammable materials. This can take from 30 minutes to 60 minutes by itself. If the battery can still hold a charge, it is used in stationary energy systems, for example, to store energy from solar panels. If the battery is completely worn out, it is sent for disposal. To monitor battery condition even before disposal, Tesla, for instance, uses its own software that can remotely evaluate the remaining capacity, the level of cell degradation, and the overall condition of the vehicle's energy system. This makes it possible to determine whether the battery can be used in secondary energy applications or must be fully disassembled. Through this approach, the company reduces the number of batteries immediately sent for disposal, extending their life cycle as stationary energy storage systems for as long as possible. The recycling of Tesla electric vehicles happens in much the same way as the recycling of other electric vehicles. But there are certain specifics due to the battery design, the body materials, and the software. Tesla batteries have a complex modular structure and a high energy density, requiring additional safety measures, including a complete discharge and controlled disassembly. A full discharge of a Tesla battery is carried out at specialized recycling centers, where strict safety measures are followed to avoid the risk of fire or explosion. This is done using special equipment that gradually removes any leftover electrical energy, placing the battery into a safe state. Because lithium-ion batteries maintain a high energy density, they can still hold a substantial charge even after extended use, making the discharge process critically important prior to further recycling. According to estimates, by the end of 2030, around 12 million short tons of spent lithium-ion batteries could end up in landfills if effective recycling systems are not put in place. To discharge the battery, industrial systems of controlled power consumption are connected, gradually drawing off the remaining energy. These machines operate on the principle of creating a controlled electrical load, simulating energy consumption, where electrical energy is converted into heat that is then dissipated by active cooling systems. Another method involves connecting the battery to industrial energy storage systems, which can use the residual charge to power facilities or feed electricity back into the grid. The process occurs in a controlled environment with low humidity to minimize the risk of corrosion and unwanted chemical reactions. The temperature is maintained between 50 degrees Fahrenheit and 68 degrees Fahrenheit because higher temperatures can accelerate degradation of battery cells, while lower temperatures increase the risk of electrolyte instability. The operator oversees discharge parameters through computerized monitoring systems, which record voltage, current, and battery temperature in real time. Once the charge falls to a safe level, typically below 1% of the original capacity, the battery is considered discharged and ready for further disassembly. The battery is taken apart, separating the casing, modules, and electronics. Each module consists of thousands of lithium-ion cells that must be properly recycled to recover valuable metals. The modules are mechanically shredded in specialized installations that operate in an inert gas environment or under liquid nitrogen to prevent spontaneous combustion of any leftover active materials. The resulting shredded mass undergoes either thermal treatment or chemical solutions to remove organic components such as electrolyte and binding substances. After processing, the recovered metals are reused in the production of new batteries, and the remaining materials are disposed of in accordance with environmental standards. Toxic waste is neutralized at specialized facilities. Currently, only about 5% of lithium-ion batteries are recycled worldwide, indicating a major opportunity to improve recycling infrastructure. One key method for recovering valuable materials is hydrometallurgy. This process involves dissolving shredded elements in specialized chemical solutions that allow for the separate extraction of nickel, cobalt, lithium, and other metals. Compared to the traditional pyrometallurgical method, which uses melting at high temperatures, hydrometallurgy is more energy efficient and environmentally safe because it allows the extraction of pure metals without significant air emissions. Thus, the batteries are disassembled, casings and electronic components are recovered, and then the active electrode material is shredded. The resulting shredded mass is referred to as black powder, as it contains oxides and other metal compounds. Next, this powder is dissolved in an acidic environment, using, for instance, sulfuric or hydrochloric acid. This stage is known as acid leaching, during which the metals convert into a solution. As a result, a liquid mixture forms that contains ions of lithium, nickel, cobalt, and other elements. The next step is extraction and selective precipitation. Using reagents such as organic extractants or precipitating agents, specific metals are extracted from the solution. For example, lithium may be precipitated as lithium carbonate or lithium hydroxide, both of which are used in the production of new batteries. Nickel and cobalt can be extracted by altering the alkaline solution or by precipitation using sulfides and hydroxides. After precipitation, the metals undergo additional purification, including filtration and recrystallization. The end products, metal salts or metal oxides, are sent back into production for new battery cathode materials. The efficiency of hydrometallurgy makes it possible to recover over 90% of nickel, cobalt, and manganese, as well as up to 90% of lithium. This significantly reduces the need to mine new resources and promotes a closed-loop battery manufacturing cycle. After disassembling and processing the batteries, the electric vehicle recycling process continues. The motor and transmission are removed if they are suitable for reuse or repair. This can be done by people manually, using wrenches, jacks, and other tools, or by robotic systems that simplify the process. Wheels, radiators, electronics, and glass are also removed, and these components can be sold separately or recycled. Window glass, for instance, is recycled by shredding it into granules, which are then used in construction or to produce new automotive glass. Plastic components, such as bumpers, interior panels, and fuel tanks, are processed by shredding and later used to create new products. Only when all valuable and hazardous components have been removed from the car do they proceed to recycle the body. It may be cut into large pieces using hydraulic shears or sent directly to a shredder. Shredders reduce the metal frame to small fragments, which are then sorted by material type. Steel and aluminum are separated using magnets or electronic sensors, after which they are sent for remelting. Those parts of the vehicle that cannot be recycled may be disposed of by incineration to produce heat energy or buried at specialized landfills. The entire process can take anywhere from a few hours to several days, depending on the type of vehicle and the level of automation at the facility. However, with modern technology, the percentage of materials that can be reused is constantly rising, and it currently exceeds 3/4 of a vehicle's total mass. Have you ever seen a ship that does not touch the water? Now, imagine that such a vessel not only exists, but can also carry tens of tons of cargo and accelerate up to 250 miles per hour. Meet the Hovercraft landing craft, a unique combat vehicle that glides above water, land, sand, and even ice. Its engines are just like those in fighter jets, and its maneuverability lets it drift on waves. But how much does this technology cost? How do they build it? And why are even seagulls afraid of these machines? Let's find out. The idea of using an air cushion came from the British engineer Christopher Cockerell in the 1950s. He experimented with airflows using tin cans and a hairdryer, ultimately creating the concept of a vehicle that could glide over any surface. In 1959, the world's first real hovercraft was launched. Later, this technology found its way into military use, specifically in LCAC-type landing crafts developed in the United States during the 1970s. So, Cockerell invented it, but the military refined the idea into its modern form. Let's move forward. Or maybe sail ahead. Manufacturing hovercraft landing crafts involves several stages. Initially, design bureaus create drawings and digital models of the craft. The design process depends on whether it's a new project or an upgrade of an existing one. Creating a completely new hovercraft takes from 6 to 12 years. Imagine that. Preliminary design and concept stages last from 1 to 3 years. Developing drawings and digital models adds another 2 to 5 years. Building and testing the prototype takes an additional 3 to 5 years. Finally, we get a ready-to-use craft. If we're talking about upgrading an existing design, the process takes half the time. Analysis and adaptation of drawings take from half a year to 1 year. Updating digital models takes only 1 or 2 years. Building and testing the updated version takes 2 to 3 years. The newest American hovercraft, called the Ship-to-Shore Connector, replacing the LCAC, began development in the 2000s. The first test models were ready in 2012 and 2014, but full-scale production started only in the 2020s. The process is lengthy because these crafts must be reliable, fast, and suitable for challenging operational conditions. After drawings and digital models are developed, suppliers of materials and components are selected. The military announces tenders, where companies compete for contracts. Manufacturers must pass certification and prove their materials withstand extreme conditions. Some components are produced exclusively domestically for national security. Thus, the process is complex, but critically important. If even one component fails, the entire mission can be jeopardized. The craft's frame is assembled at shipbuilding yards. These massive industrial complexes are usually located on coastlines or near large rivers. They cover areas from dozens to hundreds of acres, since multiple vessels must be built simultaneously, with space for storing materials and heavy equipment. There are huge covered or open areas where ship hulls are assembled. These areas can be from 500 to 1,500 feet long to accommodate large structures. In metalworking workshops, aluminum alloys for the LCAC hull are cut, welded, and shaped using robotic machines and laser cutting. Shipyards also include dry dock basins, enormous artificial pools, where finished crafts are tested before launching. Massive gantry cranes with lifting capacities from 100 to 1,100 tons move large sections of hovercrafts. Additionally, there are areas for installing gas turbine engines, radar, and navigation systems, as well as logistics yards, where incoming materials and components from suppliers are stored. One of the largest such shipyards in the United States has been building military vessels for more than 100 years. The frame assembly of a hovercraft landing craft is constructed mainly from aluminum alloys, using welding and assembly methods different from traditional shipbuilding. Aluminum sheets and profiles are supplied as ready-made blanks. Robotic machines cut out parts according to computer-generated drawings. Sections for the future frame are prepared in special workshops. The LCAC structure is not assembled entirely at once, but built from large modules. Each module, for example, the bow, stern, and side sections, is assembled separately. Rivets and aluminum welding ensure durability. The frame consists of a keel beam running the length of the craft and transverse ribs providing rigidity. Aluminum rivets and specialized adhesive mixtures are used to connect sections, reducing weight. Large modules are lifted by powerful cranes and connected precisely using laser positioning to avoid errors. At the brightly illuminated shipyard, a giant module of the future craft rises into the air. A heavy gantry crane, weighing hundreds of tons, slowly lifts the aluminum section, gleaming in the sun like the shell of a marine predator. Metal cables are stretched tight like strings, while workers in protective helmets and vests carefully monitor every movement. The enormous part floats mid-air, gently swaying in the breeze. A crane operator, sitting high above the yard, maneuvers this colossus with extreme precision. Engineers below signal instructions, guiding the module to its exact position. When the section slowly settles into place, there's a dull metallic thud. Thousands of pounds of aluminum collide with the frame. Immediately, fastening begins. Workers tighten bolts, welding machines ignite with bright blue flames, and sparks scatter from beneath electrodes. The air fills with the scent of hot metal as the craft gradually takes shape, becoming a formidable combat machine. Engineers inspect structural integrity and tightness. Attachment points for the hovercraft skirt are installed on the frame. This system must be completely airtight to maintain LCAC stability during movement. The completed frame undergoes load and vibration tests. After passing successfully, engines, propellers, and electronics are installed. Now begins one of the most critical stages. The shipyard hums with crane motors, gently transporting massive gas turbine engines, the heart of the future craft. Workers dressed in protective suits and masks precisely position them in compartments, where every millimeter counts. Simultaneously, technicians attach enormous propellers, blades made from robust composite materials, which will later propel air with thousands of horsepower. When blades rotate for the first time, air waves ripple through the air, causing fabric on work uniforms to tremble. Inside, engineers connect cables, sensors, and onboard computers, carefully inspecting every chip, screen, and controller, as navigation, communication, and automated control depend on these systems. Once everything is ready, the moment of truth arrives. Pressing the first launch button, the massive frame shudders, turbines roar to life, and the first stream of hot air bursts from exhaust channels. The LCAC is ready for its first water test. A single modern LCAC costs from $50 to $75 million, depending on modifications. Operating costs are high due to gas turbine engines and demanding maintenance. Maintenance can occur at shipyards or specialized bases. Gas turbine engines require frequent service due to limited lifespans and costly repairs. The hovercraft skirt wears from contact with water, sand, and stones. Propellers and air systems require repairs as they operate continuously at high speeds. The United States is the leading producer of the new ship-to-shore connector crafts, replacing older LCACs. Great Britain builds similar crafts for civilian and military markets. Who uses them, you might ask? The United States Navy is the largest operator, possessing about 70 LCACs and acquiring new models. Japan uses LCACs for defense and humanitarian missions. Potential customers include NATO countries and nations expanding amphibious forces, like India and South Korea. Currently, LCACs are being upgraded to SSC, quieter, faster, and more efficient crafts. Demand is rising due to threats in the Pacific region and the need for rapid troop transport. Additionally, LCACs can drift. With the air cushion, they lack typical friction with water or land, allowing them to slide sideways, sharply change direction, and even pivot almost in place, making them exceptionally agile but challenging to control. LCACs use the same gas turbine engines as military aircraft, specifically the General Electric LM-2500. Similar engines power F/A-18 Hornet fighters. Essentially, LCACs are aircraft that never leave the surface. Unlike conventional ships, they can move onto shore, cross sandy dunes, swamps, and even ice, providing advantages for landing troops in difficult locations. However, LCACs are among the loudest vessels in naval forces. Their noise can be heard hundreds of feet away, making them unsuitable for stealth missions. During operation, LCACs create powerful vortices, capable of literally blowing away seagulls and other marine birds, often making it impossible for them to remain airborne. Every year, we produce approximately 101 million short tons of textile waste, and more than half of that trash simply rots in landfills. But what if we could turn it into something useful? Imagine this: your favorite t-shirt, a stylish blazer, or even designer sneakers, all made from plastic bottles. Yes, fashion is already changing, and brands are turning waste into trendy clothing. How exactly does plastic become fabric? Why are large companies already earning millions from this? And does such clothing truly save the environment? Let us figure it out. Every year around the world, approximately 101 million short tons of textile waste are produced, of which only 15% is recycled, while 57% ends up in landfills. We need to do something about that, right? It might sound like science fiction, but in fact, plastic can be easily recycled into fabric. Let us start with the fact that most of the textiles we wear every day consist of synthetic fibers, such as polyester. Here is something interesting. Polyester is nothing more than plastic. Yes, you understood that correctly. Plastic bottles or other plastic waste can be turned into fibers that are then used to make fabrics. The process looks like this. Old plastic bottles, plastic containers, or even damaged plastic items are collected, washed, cut into small pieces, and then these pieces are melted down into new plastic fibers. These fibers are then woven into fabric that, in terms of its characteristics, is almost no different from traditional materials like cotton or wool. Now imagine this. It is not just a technological marvel, but also a chance to reduce the amount of plastic that ends up in nature. This usually happens in the following way. Plastic is sorted by type of plastic, most frequently polyethylene terephthalate, and by color. Clean and transparent plastic is more valuable because it is easier to obtain high-quality raw material from it. After that, the waste is washed in special baths to remove any remaining beverages, glue, and labels. Then, special industrial shredders equipped with sharp blades cut the plastic into uniform fragments. Sometimes water cooling is used for this purpose, in order to avoid overheating the material. The smaller the plastic is shredded, the easier it is to melt and clean it from impurities. Next, the shredded plastic is heated to about 932 degrees Fahrenheit until it becomes a viscous liquid mass. Then, this melted mass goes through special filters to remove any remaining contaminants. After that, it is extruded through fine nozzles, creating thread-like fibers. These fibers are cooled by a stream of air or water, after which they are twisted into yarn that becomes the basis for textile materials. It is impossible not to notice that fashion is now moving towards sustainability. All those popular brands we know and love, such as Adidas, Patagonia, and Stella McCartney, are increasingly using recycled plastic in their collections. However, let us pause here. What makes this plastic so popular? Environmental friendliness. As we know, plastic is one of the biggest enemies of the environment. Every year, millions of short tons of plastic end up in landfills or in oceans. But through recycling, we can reduce that impact by turning plastic waste into useful materials. And this is not just one of the eco-initiatives of brands, it is a real shift in the industry. Interestingly, some designers and brands already use textiles made from recycled plastic, not only for environmental benefits, but also for the unique look. In particular, materials made of plastic fibers can have very intriguing texture and sheen, which gives clothing a bit of an innovative and futuristic appearance. Imagine a t-shirt that is not only made from plastic, but also has a striking texture that reminds us of the future. Research shows that reusing textiles can save up to 8 short tons of carbon dioxide and approximately 164 gigajoules of energy for every short ton of textile waste. Converting that to American measures, 164 gigajoules is about 155 million British thermal units. Recycling textiles saves 5 6/10 short tons of carbon and about 116 gigajoules of energy per short ton, which is around 110 million British thermal units. That is a considerable difference on a global scale. Technology. Fabrics made from recycled plastic can be just as comfortable and stylish as regular fabrics. They even have certain advantages. They are water repellent, resistant to fading, and they hold up well to wear and tear. Moreover, if these fabrics are processed correctly, they can be made soft and pleasant to the touch. And here, we should remember another point: microplastic that can enter water through recycled fabrics. When we wash clothes, especially items made from synthetic materials, microscopic plastic particles can get into the water. However, some brands are already working on solutions to minimize this impact. For example, they use special technologies to reduce the release of microplastic during washing, or they create materials that are less prone to this. Innovation. However, it is worth noting that this is not just a trend. It is an innovation. Instead of continuing to produce more plastic, brands are finding ways to use what already exists. This opens up new possibilities for the fashion industry. For instance, one of the most fascinating technologies is recycling ocean plastic. The same plastic that is flooding our oceans can also be turned into clothing. For example, the company Parley for the Oceans creates materials from plastic collected from the oceans. This not only helps decrease the amount of plastic in the water, but also becomes the foundation for eco-friendly collections by brands such as Adidas. That is a whole different story, right? If you think that recycled plastic is something only for sportswear or accessories, you are mistaken. Imagine a stylish coat or an elegant dress made from material that was once a plastic bottle. These recycled plastic fabrics make their way onto the runways of major fashion shows and become part of refined collections. One of the most interesting examples is the Stella McCartney collection, which recently introduced a clothing line made from fabrics produced from recycled plastic bottles. And of course, you will not find any trace that these fabrics were ever anything else. They look and feel completely sophisticated. This is not merely about disposal. It is about creating genuine art out of what we used to throw away. Speaking of scale, some countries, such as the Netherlands or Sweden, have become true leaders in plastic recycling. There are even specialized factories there that transform plastic waste into textile, which then becomes part of both sports and everyday clothing. It is an entirely new approach to waste processing that not only helps preserve resources, but also creates new jobs. It turns out that the process of recycling plastic into textile not only saves the planet, but also has significant economic potential. Many small startups around the world have begun to build business models based on the collection, recycling, and resale of plastic waste in the form of clothing. Such businesses often collaborate with local communities, involving them in collecting and recycling waste, which creates new jobs and stimulates the economy at a local level. Technologies of three-dimensional printing also use recycled plastic to create fabrics. Some companies have already started making textile materials by utilizing plastic waste through three-dimensional printing. This allows the creation of entirely new textures and shapes, as well as optimizing the clothing manufacturing process. Imagine clothing that is literally printed using plastic. In recent years, the so-called smart fabrics have also been gaining popularity in the textile industry. Materials that can change their properties depending on the surrounding conditions. Recycled plastic has a role here as well. Some brands are experimenting with integrating nanotechnologies into fabrics made from recycled plastic, enabling the creation of textiles that respond to temperature or moisture, making clothing more functional and comfortable. It sounds like something from a fantasy, but there are already materials made from recycled plastic that can self-clean. They have special coatings that allow the fabric to repel dirt and water. This technology can change the rules of the game in terms of durability and convenience, because clothing made of such fabrics would require much less washing. Another exciting direction involves fabrics that alter their appearance depending on how a person interacts with them. For example, fabrics that respond to body heat or change color during movement. All of these innovations can be created using recycled plastic, opening up new opportunities in fashion. One more interesting aspect is the recycling of plastic into artificial leather. Some innovative brands have already started making eco-friendly artificial leather out of recycled plastic waste. Such leather can be used to manufacture bags, footwear, and even outerwear. This offers a material that resembles genuine leather, but without the use of animal products and with a smaller environmental impact. Here is the thing. Today's youth is a generation that is becoming increasingly aware of environmental issues. You are no longer just buying clothing. You are buying clothing that tells a story. You are buying not just fabric, but a certain idea. A future that can be more sustainable and clean. And when you wear clothing made from recycled plastic, you are not merely shopping. You are joining the change. You are becoming a part of this large movement. Of course, there are questions about the cost, quality, and availability of such materials. But do you know what? It is only a matter of time. With the advancement of technology and the growth in demand for eco-friendly products, these fabrics will become even more affordable. And that is great, because each of us can contribute to improving the situation. Perhaps in a few years, we will only wear clothing made from recycled material. And, to be honest, that does not seem so fantastic. It might become the norm, rather than the exception. And who knows, maybe in the future, even your favorite brand will use plastic waste to create new trendy items. Yes, it sounds like science, but science and fashion can accomplish many wonders together. So the next time you are choosing what to wear, think about this. Maybe it is another step toward a better world. And if plastic waste can become part of your style, then why not?